So today's lesson will be on redox reactions, and it'll be a recap of what we've done in production of materials. So in this particular option, there's a very strong focus on electrochemistry. So we're going to have to be able to deal with redox reactions very effectively, otherwise we're going to struggle to understand the various things that are going on in the latter parts of this option. That's why we're recapping it now, so that we can make sure that we understand everything for the future parts of this option. So first thing is electrolytes again. So an electrolyte is any liquid with sufficient free charge to conduct electrical current. Okay, so we have enough free charges in a solution or a liquid to allow current to be moved or to move through it, essentially. In practice, most of the time these are ionic solutions, but there could be, I suppose, molten salts, which are ionic but not a solution. So there are small differences, but most of the time we see them as ionic solutions. And as I mentioned in the previous lesson, the ocean is an extremely strong electrolyte because there's lots of free ions available in the seawater. And because of all these free ions, we see that electron transfer reactions happen spontaneously in many electrolytes, particularly the ocean. So a redox reaction. So remembering that redox reactions are reduction and oxidation reactions. And so oxidation reactions are the loss of electrons. Okay, so I like this oil rig. It's a nice little mnemonic device. So oxidation is loss, and reduction is the gain of electrons. So reduction is gain. Okay, so oil rig. Now, remembering that these words relate to the oxidation number, not actually the electrons, which is why reduction sort of sounds counterintuitive, because reduction usually means you're getting less of something when you're actually gaining electrons. But the oxidation number is actually going down when reduction happens, so that's why we call it reduction. Okay? So it sounds counterintuitive, but it's really not if you think about it in terms of the oxidation number. And remember, these reactions are electron transfer reactions. So an electron goes from one, or more than one electron in some cases, go from one species to another, and that is essentially the oxidation and reduction together happening. And these redox reactions form pretty much the foundation of all electrochemical reactions that we see in everyday life. What we do, remember, from your study of batteries, such as the lead acid cell or the dry cell, we split redox reactions into a reduction half reaction and an oxidation half reaction. Okay? So let's take a simple example. We have magnesium metal, and it goes from magnesium metal to magnesium ion and 2 electrons. So 2 electrons have come out of this magnesium atom and made it a magnesium ion, and then you've got 2 electrons. A reduction half reaction could be that the lead ion plus 2 electrons forms the lead solid. So this has oxidation number of 0. This has oxidation number of 2 plus. So you can see that it's gone down, which is why it's reduction. Okay? So the net oxidation reduction reaction is the magnesium solid plus the lead ion gives you the magnesium ion plus the lead solid. Okay? It's a very simple example of redox reactions. So it's just recapping the basics of redox reactions. So this sort of is the conclusion of this recap. So we've just looked at trying to recap on what a redox reaction is and how we represent them in chemical equations. Okay, so we'll move on to the question segment, and we'll see if we can answer the questions based on our prior knowledge. So which of the following best describes the transfer of electrons in metal displacement reactions? Okay, so it's not from one metal. So just remember what a metal displacement reaction is. It's when you have a beaker full of a solution, and then inside that beaker you've got a metal, okay, a piece of metal. And what happens is the ions in this solution come out of solution and form on the outside of this piece of metal, and the metal in here, the solid metal, becomes ionic, and goes into the solution. So they swap places basically. So obviously it can't be A based on what I've just said, because it's not an electron transfer from one metal to another. It's from what appears to be an ion and a metal. So it's not C because there's no positive electrode potential. We don't have any electrodes in there. And which of the following best describes the transfer of electrons? So from the least active metal to the most active metal. That's not very likely because the most active metals want to give away electrons. So it's probably B. So the electrons move from the most active metal to the least active metal, and the ions come out of solution. So in a redox reaction, what determines which metal will lose electrons? Well, basically it's the reactivity of the metal. Highly reactive metals will want to release electrons in order to achieve stability, right? So sodium is one example of that, rubidium, any of group 1, calcium will want to give away 2. So they're very reactive metals and they want to get rid of those electrons to become stable. However, metals that are less reactive are more likely to absorb electrons, of course when they're in their aqueous state. So when they are already ions, if they're less reactive than your solid metal, they'll want to absorb those electrons to become a metal again. So they'll return to their pure metal form, as they are likely quite stable in pure metal form. So because they're not very reactive, they should be quite stable in their pure metal form. So identify the alternative which correctly states the oxidation and reduction half reactions for this equation. Okay? So this is an example of when you would use oxidation numbers to actually solve the problem. Okay? So you got to look at things in oxidation numbers and then use your definition of reduction and oxidation to work out which is correct. So let's just ignore what's here first and just look at the equation. So here you've got magnesium solid, and its oxidation number is 0 because it's pure metal in elemental form, so it's 0. Now here, you know that the chloride ion is always -1, or in 90% of the cases it's -1. So you've got 2 times -1, which makes magnesium, in this case, 2+. So remember that, see how it's neutral, this magnesium chloride? So that means that magnesium must be 2+. Okay? So you can see that the magnesium has gone from 0 to 2+. So the oxidation number has gone up. So that means that it could be either this one or this one, because the magnesium is obviously losing electrons because its oxidation number is going up. Okay? Now which one is reducing? Well, obviously this one has +1 and this one has -1. Okay, so hydrogen is +1, chloride is -1. But here, H2 is the elemental form of hydrogen, right? So it's 0. So you can see that it's gone from 1 to 0, which means that it's reduced. The oxidation number has gone down. So it's not this one because the chloride ion hasn't changed at all. It's still chloride. So it must be this one, D. Because the hydrogen ion grabs electrons to form hydrogen gas. There you go. There you have it. It's D. So that's what we have to do when we look at redox reactions. And you should be familiar with this from your study of the dry cell and various other cells. So you should be aware of how to do this already, but this is just jogging your memory. So why is a liquid electrolyte necessary for ions to move? So why do we need a liquid? Well, if the electrolyte is solid, then there are no free charged species to carry charge and to complete the circuit. So let's imagine that you had frozen salt water. The ions are actually trapped. They can't move from one place to another. So it means that it won't be able to conduct electricity because those charges won't be able to move. And that's what electricity is, the movement of charges. Okay? So would sodium react more rapidly in either a beaker of seawater or distilled water? Explain. So the question becomes, well, the seawater, it reacts with metals very rapidly. That's why, when you have a car, it's worth less after, say, 5 years if you live near the ocean than if you lived very far away from the ocean, okay? Because the salt water attacks the steel in your car very, very, very rapidly. So would a piece of sodium react more rapidly in a beaker of seawater or distilled water? Most people think it's the seawater, but in reality it's exactly the same. Since the reaction doesn't require ion movement, and it's a direct reaction between the water and the sodium, there's no interaction between the extra sodium ions, so it doesn't really make any difference. So you would get the same reaction if you were to use seawater than if you were to use distilled water. So that concludes today's lesson on the redox reactions. So we recapped what redox reactions are and how to represent them in equations. So hopefully you're remembering all the things you learned in production and materials, because we will need that in future parts of shipwrecks. So look forward to seeing you at our next lesson.